Hello, this is All 2. I've been developing bicycle gearboxes for years. Recently, I introduced an integrated drive for electric bicycles. I realized this technology fits EVs and e-motorcycles. EVs and e-motorcycles don't use transmissions. My technology could be the solution. I will introduce this transmission technology. This shows how power is transmitted in an engine. This structure is complex, large, and heavy. This is the power structure of an EV. It's very simple. First, rotation is generated by the motor. It goes through a few gears and straight to the wheels. There is a reason it becomes this complex. It's due to the nature of the engine. This graph shows engine characteristics. The green area is the most efficient range, 1,800 to 3,500 revolutions per minute. At low or very high revolutions per minute, efficiency drops. So, a transmission is essential. It means only using the optimal RPM range. It avoids inefficient RPM ranges. However, electric motors are highly efficient. So a complex powertrain like an engine is not needed. But I have a question. I don't think this is perfectly efficient. This is a graph of the motor. The key characteristic of the motor is torque. Torque is needed when starting or accelerating. Engines have low torque at startup. This is the key difference between motors and engines. So electric vehicles have strong power at startup. Because of this, no transmission is needed across the RPM range. This is a major advantage. This is a chart of the motor. These values fall within the efficient range. It performs most efficiently between 30 and 70 kilometers per hour. However, as speed increases, efficiency drops. Efficiency reaches about 95% at its peak. At around 100 kilometers per hour, efficiency is about 88%. At speeds above 150 kilometers per hour, it can drop below 80%. And efficiency is also very poor at low speed. I am a transmission developer. I believe efficiency should be maintained across all ranges. This chart shows the concept I developed. This chart represents first, second, and third gear. A three-speed system makes most ranges efficient. This graph makes it clear. This section covers first, second, and third gear. At 50 kilometers per hour, the RPM would be too high, right? Shift to second gear to lower RPM, then speed up again. Then, when RPM rises again, shift to third gear. It drops back to a lower RPM. A three-speed system makes this wide range efficient. Once speed exceeds 150 kilometers per hour, significant resistance occurs. In third gear, output reaches its peak here. Around 150 kilometers per hour, the output is strong. It overcomes drag and tire friction. These two graphs compare cases with ICE has a narrow efficiency range and loses efficiency at high speeds. Even output decreases. A three-speed system uses a wider efficiency range. It also offers high output. Explain ICE versus EV transmission differences. Frequent shifting reduces ride comfort. An EV's third gear is completely different. Only two shift points. This is the first reason for fewer shifts. Second, high torque is an advantage. No need to shift when speed drops. It starts in first gear. It shifts to second gear at 50 to 60 kilometers per hour. Even if it shifts to second gear at 50 kilometers per hour, it shifts to first gear at 20 kilometers per hour when speed drops. That's because the torque is high. Acceleration is easy because the torque is sufficient. Runs from 20 to 100 kilometers per hour in first gear only. Shifts to third gear around 100 kilometers per hour. Even in third gear, there's no need to shift down to 40 kilometers per hour. Highways are mostly flat. 1000 Newton meters allows easy acceleration. It can run from 50 to 200 kilometers per hour using only third gear. While an ICE shifts 100 times, an EV shifts fewer than 20 times. Focused on driving conditions, not speed. Uses mainly second and third gears depending on conditions. Advanced transmissions already exist. Why isn't it used in EVs? Please translate it again. There's a clear reason. This is the transmission. The shifting system is very complex. Size and weight also increase. It's inevitable for the structure to be this complex. The concept of third gear, selecting one changes the speed. The dog clutch moves axially. Engaged with the gear, it rotates together. This is how the gear is changed. Engagement and disengagement are difficult. Incorrect engagement can cause damage. It causes noise and can damage components. Smooth engagement and disengagement is the key. Let's look at how it's applied to a dual clutch DCT. Each gear has a dog clutch. It engages the gear by moving like this. There is a dog clutch structure inside. This complex structure prevents shock and damage. Power must also be cut off through the clutch. A hydraulic system is needed to control this. A circuit is needed for the hydraulic system. This process may seem simple, but it requires complex technology. The goal is efficiency. But this doesn't seem justified. Transmission history created that mindset, but I don't think this is necessary. This is the 3-speed transmission for EVs that I designed. This side is the gearbox. This side is the motor and differential gear. The motor spins at high speed, right? These two gears here are reduction gears. The gear is selected through this channel. The belt rotates the channel to select the gear. This gear is first, then second, and this is third. The engaged gears are fixed to the shaft. The differential housing is also fixed. Integrated structure delivers power directly to the wheels. A single reduction structure has the advantage of simplicity. It seems suitable for small vehicles. This structure is a two-stage reduction gear. The reduction ratio can be split into two stages. Distributing the reduction makes the gears safer. Gear ratios are easy to adjust. So it can be used in large vehicles. This channel is driven by a belt and a small motor. Three pairs of small planetary gears are inside. Then the rotation is transmitted to the shaft. The shaft has a pole that locks the gear. I'll explain how it works. This is the main shaft. Pole is arranged as 1, 2, and 3. There are protruding poles and recessed poles. The protruding pole locks the gear, right? Four poles are fixed. When the pole retracts, the gear free spins. Let me explain the pole mechanism. The support's angle determines whether it holds or releases. As you can see, it is in the supported state. The pole can't move, right? It can't rotate like this. If the support rotates like this creates space like this. Then the pole moves like this. Then the gear can free spin. This is the real key. These are not needed. I'll explain that. Look at this beautiful stone tower. I got inspired by it. Small stones support the large one. The key is balance. This vice grip works the same way. The key is the straight alignment of the links. The camshaft matches this lower part, right? It's the cross section. When the support is aligned, it perfectly withstands the load. Same straight alignment as the rock and vice grip, right? Many people may question the durability of these pawls are commonly used in bicycles, so there's a fixed perception. But this can be applied to EVs. Bicycle poles handle impact loads. Generally, no impact load occurs when fixing the gear. So one is enough. The key is that fixing the gear and pawl increases durability. The EV powertrain. The internal motor needs a system to control speed and torque. This circuit precisely controls the motor's speed and torque. The inverter brings torque near zero and synchronizes speed. So these pawls engage safely. Then torque and speed increase. This method achieves the same effect as fixing the gear. It also has a safety mechanism. The support has flexibility. The gear can cause the pawl to move like this, right? In this case, the support does not engage. Precise timing is required. Pawl protrusion is required. This structure prevents incorrect engagement. Different from a dog clutch. This angled structure has advantages. It slips when incorrectly engaged. This structure protects the components. This support aligns instantly. It's due to the spring. Camshaft rotation compresses the springs, so this component rotates quickly. Same in reverse. Compression. The spring will align it very quickly. This pin helps with alignment. It always stays aligned. These two poles are different. This pole is symmetrical. Typical poles engage in one direction. With this slope, it becomes symmetrical, right? But symmetry is required. Use the motor's regenerative braking. This side engages for forward driver. This side is for regenerative braking. In summary, the inverter plays a key role in pole engagement. This structure prevents damage. The contact area of the pole is 24 by 2.4 millimeters. It can withstand over 1000 Newton meters. The pole is opposed from both sides, so the load is perfectly distributed 50-50. Four poles can withstand up to 4000 Newton meters. With safety margin, it handles 2500 Newton meters. This is an electric motorcycle structure. The gearbox can produce stronger torque. The top speed also increases. I'll explain it in detail in the next video. This is a structure for 3D printing. It can also be driven by a motor. This allows shift testing. This shows the speed change. I'll upload the assembly process later. Many components, it needs time.